For this next problem, I am going to do something different. So I'm going to challenge ChatGPT to a competition and see whether it can write a better solution to this problem than I can. And if it can write a better solution, that kind of means that it would liberate me from the necessity of being a software developer. I could do something more productive and fun, potentially. So I think I always wanted to assemble IKEA furniture. Um, it's more dynamic job. It's something more fun. So I could go for a swimming in the morning and later assemble a couple of IKEA wardrobes. That would be an interesting kind of thing to do, maybe. So I have this pretty advanced, the most advanced version of ChatGPT here, and I've realized it has a voice mode. So I can switch this on and see. I think it needs a couple of seconds to come on. Hi again, ChatGPT. Can you hear me?
Yes, I can hear you loud and clear. Let me know if there's anything I can help with or if you just want to chat.
So I want to challenge you to a coding competition if you don't mind.
That sounds like fun. I'm always up for a coding challenge. What kind of problem do you have in mind? Let me know the details and I'll do my best.
Do you know problem 76 from LeetCode, minimum window substring?
Oh, yes, that's a classic. The minimum window substring problem is all about finding the smallest substring in a given string that contains all the characters of another string. If you want, we can dive into it, or if you have another challenge in mind, I'm all ears.
So basically, what I want to do is I want to write this code independently, and I want to also you to kind of think about the best solution you can come up with for this particular problem. Is that okay?
Absolutely. That sounds like a great plan. We can both tackle the problem and then compare our solutions afterward. Let me know once you're ready and we can discuss our approaches.
Okay, so try to make it, try to make the solution as fast and as memory efficient as you can, and potentially also uh, the shortest and the most elegant in terms of readability. All right. So probably the first thing, let's optimize for speed first, if you don't mind. Is that okay?
Absolutely. Optimizing for speed is definitely key for this problem. I'll work on the most efficient solution I can, and we can compare notes once you have yours ready.
And I'm going to be publishing this on my YouTube channel. Is that okay for you?
That sounds awesome. I'm totally fine with that. It's always fun to see coding challenges shared and discussed. Just let me know if you need any extra info from me.
Excellent. I'm going to turn the voice mode off for a few minutes. Well, for probably half an hour or something until I can write the solution, hopefully. And talk to you soon. Okay.
Sounds like a plan. Take your time, make your solution, and I'll be here whenever you're ready to chat again. Good luck and have fun coding.
Okay. I have turned off the voice mode. So we can now look at this problem and try to find a solution, hopefully better than what ChatGPT can find. The problem is called, this is problem 76 from LeetCode, minimum window substring. And what we have to do here is basically, we have two strings, right? String S and string T. And what we have to do is find the smallest, the shortest contiguous substring inside S, which contains all of the letters from T, including duplicates. So, for example, probably what? Starting from here, we need two C's, right? So starting from here, we need two C's. So one C, second C. This B and A, we already have them here. So I think one of the options is this, right? It's this one. This contains two C's and single A and single B, right? But the shortest one, this is probably not the shortest one because this one is probably the shortest one, okay? This also contains two C's and B and A. I mean, it could contain, probably in the middle, it may contain more, even if there was another B here, so that would have some this extra B here, right? Two B's, but that's still fine. You probably wouldn't have extra things at the boundaries here, at the edges, but in the middle you may or may not have extra. Just to make clear that having extra characters basically is okay. Although because you're looking for the shortest one, you probably won't have extra characters on the boundaries. But anyway, so I'm going to propose to use a sliding window technique, okay? Which means we're going to be looking at the string through a tiny window, or maybe not so tiny. So this will be a window which will appear to be gracefully sliding from left to right. And the way it will be gracefully gliding from left to right is by the following rule. I'm gonna allow myself to move either right or left boundary, but I can only move them into the right direction, to the right. So I can never take them back. I can never move them left. Okay? Now, because I'm going to impose such a restriction on myself, that means I'm going to miss a whole bunch of substrings. And the hope is that I'm going to not miss the important ones, the ones that are potential candidates, right? Remember, something like we found this too. So hopefully at some point I'll be examining, my window will be looking at this one. Let's get rid of everything. So at some point, hopefully, my window would be looking at this. Yeah. And then at some other point, my window would be also looking at this. Yeah. If this is the case, then the rest would be kind of obvious, because every time I look at the whatever substring, if I can check if this substring is okay in the sense that it contains everything, then I can just find the shortest one of those. That's not the big deal. The whole deal is how we're going to slide this window so that while we skip a whole bunch of substrings, we're not going to skip the important ones. Now, skipping some of the substrings is going to be important because otherwise we're going to end up with at least O(n) squared solution, because that's roughly how many different substrings there are, right? If you identify each substring by two ends, left and right boundaries, I'm going to use an exclusive end. So right boundary will point to the first character that's not inside the substring. So those pairs, left and right pairs, there will be roughly O(n) squared number of those pairs. So that's roughly O(n) squared number of substrings. But if I'm going to impose this restriction on myself by only letting myself move each boundary only to the right, then I'm going to bring the complexity down to O(n), which is kind of pretty clear, right? Because since I can only move each boundary in a single direction, then each boundary, left and right, can only assume n different positions, n different indices each. So that's 2n different positions altogether, which is order of magnitude of n. Okay? So how am I going to slide this window in a way that, while it gently floats in the right direction, it never skips all of the important substrings? And here is what I'm going to suggest we do. So first of all, remember my left and right boundaries will be, so right boundary will be an exclusive end. Okay, that's how I'm going to do it, which is often useful. Sometimes produces an elegant code, slightly more elegant. Now, initially, I'm going to set both left and right to point to element with index 0, the first element with index 0, which means that is kind of an empty substring. So this is a substring which starts kind of before this element, left points here, but also ends before this element because R points to the first element that we don't need, which means it's an empty substring. Okay? So that's the beginning of my algorithm, of my loop. Now let's jump into the middle of the algorithm, right? Into a single whatever, some sort of average iteration, any iteration. So if I'm looking at this sort of substring, the whole idea is to decide what to do next. Should I increment right boundary or should I increment the left boundary? That's what I should decide. And here's what I'm going to propose. Well, so I am going to try to ensure that my left boundary is always balanced in the sense that, so the left boundary is balanced in the sense that, or let's call it stable. So my left boundary is stable in the sense that I cannot even remove a single character without affecting, without affecting any of the required characters from here, right? So for example, right now, this is balanced because I cannot remove A since I only have a single A here, but I need all of them. I need that single A because it's required. So I could not remove this character. If, however, for example, let's say left was pointing here, then this is not balanced because this character can be removed. I don't need it. Also, another situation, if I had another A here, then this A can be removed because I only need one, but I have two. And then I could also probably, removing this A also would allow me then to remove D because I don't need D at all. But then I would stop here. This is A, right? And this A I can no longer remove because I need this A. I have a single A now, and all of those single A's I need here. Okay? So that's my kind of definition of a stable left boundary, right? We called it a stable left boundary. So I will have this loop, which I will always enter. I will enter this loop with my left boundary being stable. So I'm going to call it, how should I say? Left boundary is stable. Let this be our little mark for marking left boundary being stable. So when I enter this loop, I'm going to add one character to the right. So notice that initially my left boundary is stable. When I'm going to initialize everything to the empty substring, left boundary is stable. So I'm going to enter my iteration now. And the first thing I'm going to do, each time I enter the iteration, with the left boundary being stable, I'm going to add one more character to the right. So I'm going to increment, this is actually incorrect. So before I add another character, R is pointing here. Just let me, so this is what my painting should have looked like. So R is pointing at this character. But now I'm going to incorporate this D into my substring, which means R would instead move outside to the first character outside of the string. Okay? So I would incorporate this new character into the substring. That could potentially unbalance my left boundary, right? Because since I now have added a new character, yeah, let's say I've added all of these characters and now I'm here. I've added A. This could unbalance my left boundary because now this is no longer required. I could get rid of this, and because I can get rid of this, I can also get rid of this and this. I don't need any of these. Now B, yeah, I could also get rid of B now because I have B here as well. So see, I can get rid of a whole bunch of characters from the left. So basically what that means is, so every time I enter my loop, I will add one character to the right by incrementing r. Then I will try to rebalance the left boundary if it gets out of balance, which means after I rebalance it, it will still look fine. Again, our symbol for balanced left boundary. You can probably realize this is letter L in my graceful implementation, and this is a tick mark. So left boundary is okay. And after that, after I've balanced the left boundary again, what I can do is I could see, look, I don't have any extra things from the left. So there is nothing extra from the left. Can I ask a question now? Do I, by any chance, have all of these characters with all of the duplicates inside my substring? And if yes, then I could just somehow memorize that substring or something, and then choose the shortest one out of those. That's a very simple task, right? That way, every character here gets a chance to be the last character in the substring. So wherever the shortest substring resides, every character gets a chance to be the last character there, okay? So I'm going to run this until my boundary R goes through through the entire string. If we need a kind of a proof that this will work, we may need a proof that this will actually go through all of those. This will not skip any of those substrings, any of those shortest substrings that contain all of these letters from here, including the duplicates. Let's prove that very quickly. So first of all, a quick lemma, L will always be less than or equal to R if we follow this algorithm. Not just because we called it left and right. That's not the reason why left will always be less than or equal to right. But because how we designed the algorithm, we can never, I mean, if we implement this algorithm right, remember, we're going to remove characters. So incrementing right does not threaten this inequality, first of all. This inequality starts to be right from the beginning. Left and right are both 0, and they kind of comply to this inequality. So this inequality is initially correct. Now, with each move, I am going to either increment right, which will only strengthen this inequality, or I'm going to increment left by removing some of the characters from the left. Now, that can only continue when there are any superficial extra characters, as we said. But when L is finally equal to R, that's an empty substring. So empty substring cannot contain any superfluous characters. So at that point, I should stop incrementing L. So if I implement my algorithm correctly, then L will always be less or equal to R. Okay? That's first observation. Now, the second observation would be, if this is the shortest, let's say this is the shortest substring that contains everything from here, then I would say at some point right will enter the substring, right? Because we just said we're not going to stop until right goes through every character. So right will enter this substring. At that point, left cannot be any further than the first character. It could be to the left, but it cannot be anywhere to the right. It could be anywhere here, including this first character. Okay? But the main thing is, remember, it's not going to be past the first character, because, well, if it had passed the first character, because it can never come back, then we will be never looking at this substring, right? Because when R at some point comes here, well, left is already lost. Okay, so the fact that right enters and left is not yet past the first character in the substring, that's important. The next observation I'm going to make is, well, when right finally enters, it cannot leave the substring without L also entering, because L could already be here or somewhere not yet here, but it will come in. It will come in before right can disappear. That's important. And how do I prove that? Very easy, because let's say left hasn't yet entered and right is already going to leave, right? So this is the last position. After this, right will disappear, right? This is currently right is pointing to this character, which means it's still fine. It's still fine. D is part of our substring. Now, if I follow the algorithm, can I implement right now? I can't. Why? Because when do I increment right? I increment right after I have removed all of those superfluous characters from the left. But this still contains superfluous characters. Since this substring, as we said, is the shortest substring that contains everything. So this does contain everything. So what are these extra characters? They're superfluous. So they should have been removed previously. So L cannot be right here. Okay, so that proves that right cannot disappear, right? That would be horrible, because if it disappears before left enters, then we've lost the opportunity. We can never look at this particular substring. So we know that when right enters here, left cannot be past the first character, but before right leaves the substring, left will come in. And the last bit that I need to prove to you is that left cannot budge from this position. It cannot budge from this position until right actually comes here. Okay? And if I prove that, then everything's proved. Why can left not budge from the first character? Because in order for left to budge, remember, this should be a superfluous character. So we should be able to remove this. But how can this be a superfluous character when this is when this is the shortest substring? It's the shortest substring that has everything. If it's the shortest substring, then this cannot be superfluous, because if this is superfluous, then this would be the shortest substring. Oh, come on. Somehow, so then this would be the shortest substring. Okay, so this character here cannot be removed. This A here cannot be removed because it's not superfluous. So we've proved basically everything. I think it's clear now that at some point, left and right would be looking at this particular substring, just like they are looking now. So we assumed this was the shortest substring that contained all of these. Okay. So I think we're ready to start coding, right? I mean, almost. I mean, we'll have to figure out things as we go, but so one thing that we need to start implement coding is kind of a frequency map for all of these characters. Because remember when we said we are going to remove characters from here, superfluous characters. So for that, we need to know a couple of things. We need to know how many times each of these characters need to be included. And we also need to know how many of these characters are currently included. Okay? All right, so I think we can start coding on this. Let me copy this function to a slightly better editor. This is typescriptlang.org. So I'm going to paste this here. Let me make it more spacious. Okay, we have, yeah, let's keep it like this. Right, so first of all, let's start by creating a frequency map for this, for the target. So I'm going to call this need, and that will be new array of numbers. So because I'm going to optimize everything for speed, okay, the way I'm going to do it, so for each code, let's say this letter A has code, I think, what, 97 or something. But I know that the code is somewhere between 0, so the code is somewhere between 0 and, between 0 and 128. It's in this range somewhere. So I'm going to create an array that has indices from 0 to including to 127. Okay. And it's going to contain some extra kind of slots, which will remain unused, but that's fine because I'm optimizing for speed. If I later need to also optimize this for space, then I could kind of do that. But this is going to be very fast. And because ChatGPT is also thinking now about a very fast solution, probably, I need to optimize this as much as I can. So instead of using map or something like this will be the fastest thing I can think of. So if I take an array with 128 elements and fill it with zeros, so I'm ready to populate this now. So now now I've just filled this with 0. So it just contains 0. So I have to go through this string. Okay. And the way I'm going to go through this string, you know what I'm going to do? I'm going to go in the reverse order in the string. Again, for speed, I'll explain what I mean. So let I equals t length minus 1. I is greater than or equal to 0 minus I. Okay. So I am going through t through each index of each character in I, but in reverse order. Why? Because if I go in the ascending order, then t length will be here. So I'll be calculating t length here. So I do not want to query t length multiple times. Again, I'm sure that the compiler would be able to optimize this away, but I just need to be sure that I can use every trick that I know because I'm competing with ChatGPT currently. Okay, so I'm going to go through the string in a reverse order, and I'm going to say what? Well, so t character code at position I, that is the character code of the character at that particular position I, right? So now I have to go inside that slot in need and increment it. Remember, this is set to 0, so I can confidently increment it. I'm going to use pre-increment because it's faster. Again, compiler will be able to optimize this away even if I do post-increment, but I'm going to do a pre-increment. Okay, so now need is fine. But we also said we're going to need not just how many we need, but also how many we have currently. Okay, so I'm going to also initialize that have new array, very similar array, number 128, and I'm going to pre-fill it with zeros. So very similar array, but it will remain filled with zeros for now. Okay, so I have some certain things ready now to enter my loop. to enter my loop. Remember, we have to initialize left and right to 0. So I'm going to initialize left is 0, right is 0. And then I'm going to say while. So how do I enter this while? While, remember what we said? I'm not gonna relent. I'm not gonna stop until right goes through this entire string. Okay. So what I'm doing inside this loop, I am going to be adding a next character. So the last time I come in, so the last time I come in is when right is pointing here. Okay. So when right is pointing to the last character, this is right. That's when this character is actually not yet included. So if I come in with this setup, when right is pointing to the last character, I will then include this character and move right to point, beyond the string. So I can reflect this now in my loop. While right is still less than s length, right? That means the last time this will happen is when right is pointing to the last character with index s length -1. So this is great. Now what I have to do is, well, why don't I remember the code of that character? Yeah, when I add one more character, I need to know the code of this character. So before I increment right is actually pointing to this character. Remember, I'm using exclusive AND. So s character code at right. But now I can instantly increment right. Yes. So this is post increment. So I'm going to take code of this character and then also instantly increment right. So together, this is kind of part of this header in some sense. This works together with this header. Yeah. So now my code is there. What do I have to do with this code now? So first of all, remember this array have. Every time I add a new character or remove an existing character, I have to update count for each of these characters. So currently I have added new character with this code. So I have to say have code ++. Okay, I've incremented the count for how many characters I have with this code. Great. So what should I do now? Now I should start removing characters from the left side. So I should start removing these characters. To remove these characters from the left, what should I do? I should do the following. Let me do a for loop here. So I'm going to organize this into a for loop. And I'll try to explain why I'm trying to do that. Because, let me say it like this. Let's left code equal to s car code at the left position. Okay? So this is the code of the character that maybe potentially be removed. Potentially. Now, that potentially will be reflected in this condition that I'm going to write here. So when I am allowed inside this loop to remove that character, well, have of L code must be strictly higher than need of L code. So this is the code of that leftmost character. And if I have more of those characters, then I need them strictly more, then I can enter this loop. And then I'll probably remove it. And then let me also write the increment here. So what I have to do is left needs to be incremented, but also L code should now point to the code So L code should become scar code at this point, but I think it needs to be pre-increment, right? So what this will do is basically increment my left, okay? Well, when this will work, first of all, when I've already been inside the loop, I've removed the character with index left. So now first left will be incremented to point. So I've removed this character, yeah, inside the loop, but left is still pointing to that removed character. So I will have to increment, well, pre-increment left, and then use this incremented value to get the code of this next character, right? Yep. So, and this will go into L code, left code. That's good. So every time I come into here, left code is the code of the character that needs to be removed. And I know that it has to be removed because if I came into this loop, then this condition, this allowed me, this guard allowed me into the loop. So this character is superfluous. If this character is superfluous, I have to do have of L code needs to be decremented. Yeah, that is correct. Have of L code, it's L code. Yeah, because have operates on codes. Have is indexed by codes. So have of, so now you can probably see why I used for, because it kind of takes care of this entire thing. Plus also this L code, the variable L code is not visible outside, and it kind of ensures that I don't have to calculate the code of this character multiple times. It's stored here and it's used. You can see L code is used a lot. So this for loop organization is much better than a while loop. While loop would have been not as if it wouldn't have looked as nice as this one. Okay. So after this, my left boundary is balanced again. So what I did, just to summarize, yeah, just get rid of a whole bunch of stuff here. What did I do? So inside this loop, what I did was, so I'm here, I have added, you know what? Let's do it like this. So I was here, I have added this character. So I've added this character. Then potentially I have removed a whole bunch of characters, maybe even this B, E, not C. So I've removed all of these characters. Yeah, so now I'm basically looking at this kind of substring. So this boundary is now balanced again because this character cannot be removed. This character is not superfluous. But now I have to check, well, wait, this character is not superfluous, but by any chance, is this a substring that contains everything from T? How do I do that? Now, to do that efficiently, I mean, I don't want to kind of go through this substring and kind of count everything, etc. So why don't I do something like, well, if I knew how many unique characters, I have. So here I have a frequency map, right? I have a frequency map. So I know that I have one of A. So I have something like, remember need, we called it need. So this looks like A, B, C, D, etc. And also previous codes. It's codes though. It's not these letters, but it's codes. But so this one is 1, 1, C is 2, D is 0, and all of these other ones. So lowercase z is 0, all of this stuff. So I have this. But what I need is how many unique letters are here. Now, I could count this by going through this array, but this array could be very long. So why don't I go through this need and quickly count how many elements are greater than 0? Okay, that would be the number of unique characters. So, and I'll tell you how I'm going to use the number of unique characters. So constant unique characters equals to take need and reduce it how? So we're going to start from 0. We're going to start counting from 0. So we have initially 0 characters with, 0 unique characters. Now we're going to see some sort of total. So this 0 will go into this total initially. And then the second parameter here will be the count for that particular character, right? Character count. Remember, this is, say, for example, for letter C, it's going to be 2. So this will be 2, right? And I don't need an index for this or anything. So which character doesn't matter. I just need to know how many characters. So I have to say total plus, that's what I'm going to return. Well, count more than 0. So this is a Boolean, which is 1 or 0. So this is technically correct. Although TypeScript will not let you. I mean, you could make this work. Yeah, if you really wanted speed, you could say as unknown as number. You could do that. But you know what? This is just too ugly. Even this is just so ugly. I'm just gonna do it like this. So if count is more than 0, then 1, otherwise 0. Okay, so we'll just convert this Boolean. We'll just convert this Boolean into a number, 0, 1. So this reduce should basically give me the value of unique characters inside this need array. Yeah, yep. So that's our unique characters. Now, I'm going to use unique characters. If I know how many unique characters I have, so I have 3. Okay. Now, what I'm going to do is every time I add a character to the right, I am going to say, well, after I take this into account, have I reached, so have I now, the number of characters that I now have, is it the same as the number that I need? Okay, so have I basically ticked off this particular character? Right? So have I fulfilled the requirement just for this character? And if I have fulfilled, then I'm going to increment. So I'm going to have a new variable, something like, let's call it, wow, this is slow, ticked characters. How many characters I have fulfilled or ticked characters. So I'm going to increment this if I have ticked off this character. Okay, so currently I have 1B and I only need 1B. So ticked characters will go up. Now, next time I see B, okay, it will no longer go up because this time it will be already over B. It's not going to be. So I'm going to only increment ticked characters when I just go over the threshold. So notice also that I'm never going to, if I tick off a character, if I fulfill the requirement for a character, I'm never going to go down again on that character ever again. Because of the way I'm removing the characters. I'm only removing characters that are superfluous. So I'm never going to remove any character that is needed. So if I ever say that, well, this character tick, this is good. And then I'm going to increment this. I am never going to need to decrement ticked characters ever again. Yeah. Sorry, that was slightly confusing, but so unique characters here, and then also let's say let ticked characters equals 0. So ticked characters equals 0. But when do I increment it? So I never decrement it, but when I think after this, right? So I've added a character, I've incremented the have, the count for this character. Now I have to say if have code is precisely equal need for this code, then I need to do what? Then I need to increment ticked characters. Okay, makes sense? But now I can optimize these two lines. Is that an optimization? Yeah, why don't I optimize it? So I'm not sure whether this will actually produce any speed optimization, but again, the competition is ruthless with ChatGPT. It's very smart, the latest model, if you remember. So just in case, why don't I just optimize this? So have plus plus. Why don't I move plus plus here? So if I just do it like this, it's going to be the same, right? So I'm going to take have code, pre-increment it, and then I'm going to compare it to this. Yeah, this is good. Yeah, this is fine. So now here, basically, let's put a small command, remove also, not, we don't need all. All is superfluous. The word all is superfluous. So remove superfluous characters from left. Here we have add character to the right. Remove superfluous characters from left. Now, ticked characters is correct. Ticked characters will contain the number of characters that have been ticked. And if it is similar to unique characters, if it's exactly the same, if ticked characters is the same as unique characters, then I have to do something. What should I do? Well, I need to have min length. Okay, so let's have minimum length, which initially will be set to plus infinity. Okay, and also, okay, plus infinity. So if ticked characters equals unique characters and right minus left, which is the length of a subarray that I'm looking at, because right minus left with this right being exclusive end, this is precisely the end, the size of the subarray, the length of a subarray. If this is smaller than min length, then I enter here. And what I do here, I just have to remember that substring. But I do not want to reallocate the substring or remember or just copy it or anything. So what I'm going to do is just remember the boundaries, left and right boundaries. I'm just going to remember left and right. So min length and also left and right, which will be equal to -1, -1. So I'm also defining two variables here. Yeah, I'm going to define them like this because I'm going to use them like that. Right? So L and R will be -1 and -1, kind of indicating that so far I haven't really found any left and right boundary. But here I have. So what I'm going to do is two things. Left and right will become left and right. Yeah. Okay. And also what I need is mean length must become right minus left. Yeah, instead of, so I'm not going to write R minus L. I'm just going to do right minus left. And the reason is because then I could move these. This will, just by accident, I move this up. It will remain correct. Yeah. Okay, so I did that. That is getting close to end. So now I can take care of this red squiggle and get rid of this red squiggle by actually returning something. Now return. If mean length is still infinity, then I should return an empty string. Otherwise, I should return what? S substring. S substring what? Left and right. Yeah, left and right. Now, right is exclusive end, but substring also uses exclusive end. So this is good. So if mean length is still infinity, then I do this. But you know what? Since I have this -1, if I do substring with -1, this will be an empty string anyway. So I could further optimize. I mean, this is not going to be good. This is, so I'm going to do it like this. So I'm going to lose this information that, I mean, here, this really clearly tells the reader that, I mean, infinity here is a special case, reminds us that we had this infinity, and but I'm going to make slightly worse code, but again, optimize for speed. This is it. Let me also, you know what, get rid of the comments. Why, I don't know. I'm just, yeah, I'm going to try this now. Let's make this slightly smaller. And I'm going to paste this here and try to run it for pretests. Oh, okay, so all of them passed. All right, the big moment, I'm going to submit this. I am going to submit this and see what's going to happen. Okay, so this passed. Let me take a screenshot of our verdict. So I am going to try to take a screenshot of this. Okay. Because we have to compare this with, okay, this is very slow. Come on. So I'll be comparing this with ChatGPT, right? So I have, okay, let me just take this out. Right, it's time now to go back to ChatGPT and say if it's ready to produce that code. Let me go back to the voice mode. Wait for ChatGPT to wake up. ChatGPT, can you now produce the code for that problem that we discussed?
Sure, I can definitely share a solution for the minimum window substring problem. Here's a Python solution that uses the sliding window technique for efficiency. It's min window substring, if you don't know. From collections about or counter, if you don't need it. Dict is counter is basically counting your characters. Falso needs a falso here. So from the
Okay.
collections that we use.
Listen, can you produce a solution in TypeScript, but don't give me an explanation at this point. I just want to test it. But remember, you have to optimize it because this is a competition, right? Optimize it for speed above everything, and then for memory, and then for length and beauty, etc.
Got it. Here's a TypeScript solution for the minimum window substring problem, optimized for speed. Function min window SG if you like. If T length is 0 or C length is 0, rather, we go. The dict T is empty. Our dict T is empty. For most of us, probably just one
Okay,
character.
so,
So maybe I should.
let me just have a look at the code and see how it performs. So I'm hoping that so somewhere I should have a TypeScript solution now. Oh, so I have to let it finish. Okay, wait. So that was a Python solution, but ChatGPT, can you produce the TypeScript solution for that problem without lengthy commentary how it works?
Got it. Here's a concise TypeScript solution for the minimum window substring problem. A function called min window x. Give just a minute. Here we go. The dict T is in different forms, and we need exactly k characters in our number counts. So window counts has to match required. So the point of the game is basically finding the smallest window. Window counts evens out with any additional help. We've already met that requirement. Then just save a minimum size time when the window is closing. And then as things loosened up, we're back here around the beginning. So hopefully that, gets you started with your solution.
So remember, we are competing. I already have my solution, and you have to show me your solution so that I can compare which one is faster. I'm going to be submitting both to LeetCode and identifying the faster solution, basically.
Got it. That solution should be pretty efficient, and I'm excited to see how it compares to yours. Good luck with running the tests, and let me know how it goes.
Okay, let's turn off the voice mode. So do I have a TypeScript solution? Yeah. So this is what? This is the TypeScript solution, right? That sounds correct. Min window. I can copy this. Okay. So I copy this and paste it to here. Now, I'm going to paste it into here, and I'm going to say with a comment, this will be so solution by ChatGPT 4.0. Let's run it on pretest and see how ChatGPT does on the pretests. Okay, not surprising. So how about if we submit it? So let's submit it. So our solution is beats 90, so 18 milliseconds. Oh, damn. Wow. ChatGPT, my solution is better. So your solution, right? So I'm not talking to ChatGPT right now. So ChatGPT solution took 28 milliseconds and beat 56%. Mine took 18 milliseconds and beat 91%. So ChatGPT's memory usage is 61 megabytes, beats 39%. Mine is slightly less, 59 megabytes, and beats considerably more, 78%. Wow. So here, the comparison is pretty clear. I think we defeated ChatGPT very clearly, very clearly. Now, in terms of the clarity of the code, so I haven't included any commentary or anything. Now, let me just look at the code. So this is our code. And why don't I duplicate this? and just replace my, whoa. I think even, I mean, this is tiny compared to what ChatGPT came up with, right? Let me just get rid of every additional extra line here so that, sorry, whoa, sorry. I just need to get rid of empty lines so that we can roughly compare so that it can fit on the screen, but it really still doesn't comfortably fit on the screen for me. Yeah, so that's that. And this is my solution. Okay, so I think I prefer my code. There are no commentary, but I mean, my code looks less daunting. I mean, this is, whoa, what's going on here? Window counts. Okay, so that's a map of string of number. Okay, I get it. But what is that? If answer 0 equals -1, then this. So, so this is min length, mm, which is initialized to -1, probably. No, it's not going to be min length. How is it going to use this? Ah, right. So it is min length, but instead of infinity, it initializes it to -1, and it's every time it's saying whether it's still -1. Yeah, well, infinity is better solution, right? Okay, I mean, this is doable. Okay, I kind of understand what it's trying to do. Left plus plus or right plus plus. This, well, I'm happy with my solution. So, unfortunately, at this point, I cannot quit software development and cannot become IKEA furniture assembly engineer. So I'll probably have to wait for next issue of ChatGPT. If it can liberate me from software development so that I can do more swimming and something more interesting, yeah, then I mean, look, if we just remove extra lines here, I mean, this solution is tiny. Yeah, definitely I have to keep doing software development for a couple of more months at least, waiting for ChatGPT to get better. Okay, well, let me thank ChatGPT. I just want to wait for ChatGPT to wake up. And ChatGPT, thank you for being a good sport. Thank you for your solution. I think your solution isn't faster or more memory efficient than my solution. So I think you lost this challenge, but thanks for playing this. And it was really fun playing with you.
I'm glad you have fun. That's what matters most. And hey, a little friendly competition is always a good way to learn and improve. If you ever want to do something like this again, just let me know. Congrats on winning this round.
Thank you. Thank you very much. That was great. Thank you very much.